So here we'll look at the idea of maximum likelihood just from a very practical perspective using a simple example. And with these 5 steps, you can do the majority of MLE type questions. And so the idea is we are given a particular distribution and we have a random sample. And with this information given to us, we need to find the maximum likelihood estimator. So if lambda is your parameter, we want to find lambda hat, which is your MLE. Okay. So if we start this off, we derive this quantity called L, which is your likelihood function, and all that you have to do is think of what the probability mass function is for a Poisson random variable parameterized by lambda, and then we take the product of those mass functions for each of your x1, x2, all the way through to xn. So from any textbook, you'll see that the probability mass function for a Poisson random variable is e to the negative lambda times lambda to the x over x factorial. And because we're doing this for all n of our observations, we have to look at each individual xi and take its product from I equals 1 to n. Okay. The next step in this process is to find the log likelihood, and the log likelihood is just the log of the likelihood. So basically all that I do is I just apply the natural log to this whole quantity here. So I can say L is equal to the log of the likelihood, which is nothing but the log of this. Cool. Like that. And so what happens now is that the reason why we do this in the first place is that it can be proven that optimizing log likelihood is identical to optimizing likelihood. You get the same like lambda hat value in this case. And another reason why we do this is because we're eventually going to apply differentiation, and to differentiate a product is complicated. To differentiate a sum, which this converts to, is not complicated. So if we take the natural log of this, we get, the log of a product becomes the sum of some logs. So what we get is the sum from I equals 1 to n. And this becomes, let's log the first term. So that's ln e to the negative lambda. This timesing makes it addition. So plus ln lambda to the xi. And then the division here turns it into a minus. So minus ln of x sub I factorial. Cool. And so this is L. We can carry on. So we know that this is the sum from I equals 1 to n of, well, the lambda comes down the front. So that becomes negative lambda ln of e. ln of e is just 1. And this is going to be plus x sub I comes down to the front. You're left with ln lambda minus ln x sub I factorial inside there. Okay. And that is L. Now what we can do is we can take the derivative with respect to lambda. So let's find del L on del lambda. And this is, well, differentiating each of these terms, what we get is the sum from I equals 1 to n. The derivative of this with respect to lambda is negative 1. The derivative of this with respect to lambda is x sub I over lambda, using just log differentiation rules. And the derivative of this with respect to lambda is actually just 0. And so what we do is we set this equal to 0 for stationary points. Now, I'm not going to say for max just yet, because we have to actually show that this isn't a min, and it is in fact a max. So what I can now do is I can sum each of these individually if I want to solve this. So this becomes the sum from I equals 1 to n of negative 1 plus the sum from I equals 1 to n. Well, I can take the 1 over lambda out because it doesn't have any I subscript on it. So what I can do is I can say like that and just sum your xi's. And the xi's do have a subscript, so you have to leave it in the summation. And we'll set that equal to 0. The sum from I equals 1 to n of negative 1, you just take negative 1 plus negative 1 plus negative 1, so you get negative n if you do it n times, plus 1 on lambda. Now the sum of xi, we know that if we want to compute a mean, all that we have to do is take the sum of the values and then divide by the number of values. And so if we times both sides by n, we get nx bar is equal to the sum of all of your xi's. So basically another way I can write this is just nx bar equal to 0. Cool. We can divide by n everywhere, so what this becomes is -1 plus 1 on lambda x bar is equal to 0. What we can now do is times by lambda everywhere, so timesing lambda here, we get negative lambda plus x bar is equal to 0, and now we get our lambda hat according to maximum likelihood estimation is just nothing but x bar. Okay, so this is your maximum likelihood estimator. All you do is take the mean of x, and to show that this is now a max, what we have to do is look at the second derivative. So what we can do is we can take a look at what del L on del lambda was. So del L on del lambda was this, right? So we had, let me write this just another way. So del L on del lambda is equal to -n, and then we saw that this one here was plus 1 on lambda times the sum of x bar, which was just nx bar. So if I just rewrite this, we get -n plus nx bar lambda to the -1. Might be easier to see it like that. Okay, and so what we now have to do is take the second derivative with respect to lambda. So del squared L on del lambda squared is equal to, with respect to lambda, that derivative is 0. And if we take a look at this derivative, this becomes negative nx bar lambda to the -2. So in other words, we get negative nx bar over lambda squared. Cool. And we know that this is negative, which means we have a max, which means that our lambda MLE is in fact a global maximizer of your log likelihood. And the reason why we know this is negative is because all of your xi's are non-negative and your n is positive, right? N is just the number of things in your sample here. And then your lambda parameter, according to Poisson distribution, is also a positive quantity. So that's how we know it's in fact a maximizer. And that's how you do it. So you get your maximum likelihood estimator and then just show afterwards that it is in fact a maximizer.